In this video, we will talk about monotone and Cauchy sequence. I have the definition of what it is for a sequence to be convergent here for your reference. We will be talking about monotone sequence, monotone convergence theorem, Cauchy sequences, and then the Cauchy convergent criteria theorem. We will start with monotone sequences. A sequence of real numbers Sn is increasing if Sn is less than or equal to Sn plus 1. In other words, subsequent terms in this series are bigger or equal to previous terms. And it is decreasing if subsequent terms of the series is less than or equal to previous terms, or Sn is greater than or equal to Sn plus 1. And a sequence is monotone if it is increasing or decreasing in this fashion. And by monotone, it means that the sequence doesn't first increase, decrease, and then eventually settles down into increasing. What monotone means, it is constantly increasing or constantly decreasing. Examples of monotone increasing sequences include an is equal to n, bn is equal to 2 to the n, and c equals 2 minus 1 over n. And I have written the first few terms here, and you can verify that every subsequent term is bigger than the ones before. The sequence 1, 1, 2, 2, 3, 3 is also monotone increasing, and I have that sequence here. Last, the sequence 1, 1, 1, 1 is also increasing because it satisfies this condition that every term is bigger than or equal to the previous terms. In particular, in this example, every term is exactly equal to the previous terms. Examples of decreasing sequences include 2 over n and minus 3n, the first few terms I have written here. Also, un is also a decreasing sequence as well as an increasing sequence because it satisfies this condition here that every term is less than or equal to the previous terms. In particular, it's exactly equal to previous terms. Then the last two sequences we have that are not monotone include -1 to the n, and it bounces around because of this alternation of the negative and positive sign. And then the cosine, which I didn't write out the terms, but we know that the cosine is periodic and is kind of a waveform. So neither of those are monotone increasing or decreasing. Next, we have the monotone convergence theorem. A monotone sequence is convergent if and only if it is bounded. In our examples over here for increasing and decreasing sequences, we can see that Cn is bounded, and it's bounded by 2. And you can see that in the formula, which is over here. As n gets bigger, the 1 over n gets smaller and closer to 0, so essentially we're approaching 2. We can also see that Sn, which is over here, and I have graphed it down here, is bounded by 0, and you can see that because as n gets larger, this value here is getting closer and closer to 0. And then un is also bounded. Un is, since it's constant at 1, it's bounded by any number greater than or less than 1. The monotone convergence theorem does make intuitive sense in that if something is monotone increasing, it's not going to converge if it keeps growing unbounded. So to be convergent, it also has to be bounded, similar for a monotone decreasing sequence. But we will look at the proof, the formal proof of the monotone convergence theorem. Because it is an if and only if statement, we have two directions to prove. We'll start with the forward direction. We will assume the sequence is convergent. In other words, the limit of S of n is equal to S, and we want to show that the sequence is bounded. Since it is convergent, we're going to use this definition of convergence that I have included up here for your reference, and we're going to say we can choose any epsilon. So we are going to choose epsilon equals 1 because it's an easy number. And since it is convergent, by this definition here, it means there's a natural number capital N, such that for all natural numbers little n greater than or equal to capital N, we have Sn minus the limit is less than 1, the epsilon that we have chosen. Since 2 videos ago we kept proving that things were convergent and then we would solve for n in terms of epsilon, it's really tempting to do that here, but we're not proving convergence. In fact, we're assuming it's convergent, but we will take note that this statement here is true for all natural numbers little n greater than or equal to this capital N, which we can find. Manipulating this part algebraically, I can get rid of the absolute values by letting Sn minus s be between -1 and 1, and then I can add s to both sides to get Sn is between s minus 1 and s plus 1. And to kind of show you what is going on here, because I can't really visualize a lot without an example. So if I look at this statement, Sn is between s minus 1 and s plus 1, so I've written this here. I've taken the case when s is greater than 0. For example, s is equal to 2, then this statement says Sn is between 1 and 3, plugging in the 2. I would get 1 and 3. If s is less than 0, let's say s is equal to -2, now I get the value for s1 is -3, and s plus 1 is equal to 1. So in this case, where s is positive, I have the absolute value of Sn bound by 0 and s plus 1, the 3 value. But when s is negative, I have Sn now bound by 0 and the s minus 1, the -3, because I'm looking at the absolute value, s minus 1. So that's why there are these two cases here, because we don't know if s is positive or negative. But in either case, we have a bound. So Sn, the absolute value of Sn, is bound by the max of s minus 1 and s plus 1 for every, and again, the conditions for this was that we have little n is greater than or equal to capital N. So the sequence is now bounded for all natural numbers greater than or equal to capital N. But what about the natural numbers less than capital N? Are they bounded? We are going to use the fact that Sn up to this little n is a finite set. Sn doesn't have to be finite, but once we choose a capital N, then we have a finite set. And every finite set of real numbers has a maximum. We'll call that maximum capital S. So now we're going to have Sn, the bound of our absolute value of the series, as S, absolute value of S plus 1, absolute value of S minus 1. And we're going to call this maximum M for all natural numbers. Sn is bounded. And I don't think I've seen a theorem for this, but we're going to say if the absolute value of Sn is bounded, then Sn is bounded, and we're going to use that without proof. Now we will do the opposite direction. We're going to assume that our sequence is bounded, and we're going to look at an increasing sequence. The decreasing is going to be similar. And we want to show that the sequence converges. So we're going to start with capital S denoting our non-empty bounded increasing set S sub n. By the completeness axiom, which I have copied here, that says every non-empty subset S of R that is bounded above has a least upper bound, then S here is going to have a least upper bound, the supremum, which we'll designate with S. So S is equal to sup of S, and we're going to claim that the limit of our sequence is equal to S. I have this little drawing here that we're going to kind of reference later. So this is my set S, and I just made it an open set. So this S is supposed to be the capital S denoting the set. This little s is the sup of my set S. Now, 2 videos ago, if we wanted to prove that S, little s, was the limit of Sn, we would then go and solve for n in terms of epsilon. But in this case, we don't have a formula for Sn, right? This is a generic Sn. It's not a particular sequence. So we can't do that approach here. We're going to have to do something else. We're going to have to rely on some things with the sup of S, the fact that, well, we have the completeness axiom that we're going to use to get to this final condition here where Sn minus S, the absolute value of Sn minus S, is less than epsilon. And we'll start by saying, given any epsilon greater than 0, so we're kind of trying to go along with our definition of convergence. Given any epsilon greater than 0, S minus epsilon is less than S, right? Because here we are at the sup, if we subtract something, well, this is kind of obvious. Anyway, so an S minus epsilon is not an upper bound of Sn, and we know that because S is the sup. It is the least upper bound, which means there exists a natural number n such that Sn is between, it's less than the sup, but greater than S minus epsilon. So maybe we have some distance epsilon here and S minus epsilon is here. Then there's some S of n that is between or maybe even equal to the sup, right? So it might be S, but there's some Sn less than or equal to the sup and greater than S minus epsilon. And since Sn is increasing, we know that Sn is greater than or equal to S capital N as long as little n is greater than n, which means that S minus epsilon is less than S capital N, which is less than or equal to S little n, which is less than or equal to S, our sup, which is less than or equal to, or less than our sup plus epsilon. And again, this is assuming n is greater than capital N. Pulling this part of our inequality, this term of our inequality here, and this last term of our inequality here, we have Sn is between S minus epsilon and S plus epsilon for all n greater than or equal to capital N. In other words, Sn minus S is between negative and positive epsilon, which gives us our final condition, Sn minus S, absolute value of Sn minus S is less than epsilon, which is exactly what we needed to show for convergence, and the limit of Sn is equal to S. Now that we have the theorem proved, I want to go back and just look at some of the 3 critical steps we did to get this theorem proved. First, we used the completeness axiom to get S is equal to the sup of S. In other words, we did that right here in this step. By completeness, we said that our set S has a least upper bound. Second, we introduced epsilon, some epsilon greater than 0, and that's because we needed to do this to start looking at our definition of convergence. We need epsilon greater than or equal to 0. So we introduced that right over here in this step here. And then we started comparing that epsilon. Well, we subtracted it from S, and we compared it to a typical Sn and our sup right over here. And then last, we used the fact that S was increasing in order to introduce our capital N and a little n, and we said that S of capital N is less than or equal to S of little n. Once we had that, we can introduce those two here. S of capital N is less than or equal to Sn if n is greater than or equal to n, capital N. And then we have these statements here. We said that S minus epsilon, because this is the upper bound minus epsilon, it has to be less than S. And between S plus epsilon, we took the parts of this equation then that we needed in order to finally get to Sn, the absolute value of Sn minus S is less than epsilon. And then just to remind you that this is for monotone sequences that are bounded, we can look at an example of a bounded sequence that is not monotone, that does not converge. And how are we going to find a sequence that does not converge? Like, what are the conditions? Where we're going to negate the definition of a sequence that does not converge, and that'll give us the conditions we need to look for. Here, I have translated the definition of what it is to be a convergent sequence. That is, there exists some S. There's some real number S that for every epsilon greater than 0, so for every epsilon greater than 0, there exists a natural number n, there exists n in the natural numbers such that for all natural numbers little n greater than capital N, that will imply, and then I have my Sn, absolute value of Sn minus S is less than epsilon. So I want to negate this statement, and so using our negation of quantifiers, my there exists become for all, and my for all become there exists. So for all S, there exists epsilon greater than 0 for all n in the natural numbers. And now I'm going to negate this part here, that n greater than or equal to capital N implies the absolute value of Sn minus S is less than epsilon. So I did this extra step here, which you could ignore, so I'm going to cross it out. But to negate then this implication, to negate an implication, you take the hypothesis and then you AND it with the negation of the conclusion. So I ANDed it, and here's the negation of the conclusion. I flip the less than sign to greater than or equal to. So this is the negation of this definition of convergence. So anything that satisfies this diverges. So what we have is that a sequence diverges provided that for every real number s, for every natural number n, there exists an epsilon greater than 0 such that n greater than or equal to capital N and Sn minus s, absolute value, is greater than or equal to epsilon. And the fast so maybe that was just a big exercise in negation, but now you do know how to find the definition of divergence. We can consider Sn is equal to -1 to the n, and that just alternates between -1 and 1. So you can see that this is bounded because everything is less than or equal to 1. It's certainly bounded, but you can see that it does not converge. So this satisfies the condition of a divergent series. And I've written that here. This sequence here satisfies a sequence that is bounded but does not converge. Next, before we do examples of proofs using the monotone convergence theorem, I'm going to tell you the proof strategy is you want to show your sequence is monotone and then bounded. And if it's monotone and bounded, you can say it's convergent. So to show that a sequence is monotone increasing or decreasing, and that it's bounded, often you're going to have, like in this example, you're going to have a series where you have S1 defined and then Sn plus 1 defined. So this is kind of a recursive definition. In other words, subsequent S of n's depend on the previous S of n's. So when you have this sort of recursive definition, then it's natural to use induction to show the sequence is both bounded and monotone. So you'll see this over and over. We're going to use induction to show the sequence is bounded and monotone. Then we're going to use the monotone convergence theorem to say that it is convergent. Last, when we actually want to find the limit, we're going to use this fact here. And you'll see that a couple of times in the next example. Our next example is to use this theorem, which is we have a sequence Sn defined by S1 is equal to 1, and Sn plus 1 is equal to 1 plus Sn to the 1/2 for n greater than or equal to 1. So we're going to show that Sn is a bounded increasing sequence and therefore convergent. So we're going to show it's bounded, we're going to show it's increasing, and then we're going to use this theorem to say therefore it must be convergent, and then we're going to find what Sn converges to. We are going to start by showing that it is bounded. First, we kind of have to have some idea what its upper bound is. To that end, I started writing terms of the sequence. So I have S2 is equal to 1 plus S1 is 1, so square root of 2. Then I have S3 is equal to 1 plus square root of 2 all square rooted. And then I did a few more terms, which I didn't write all of them down, but it appears the sequence is bound above by 2. And we're going to prove this using induction. I moved my work aside here, and again, this is what I want to prove, that Sn is bounded above by 2 using induction. We have our base case that n is equal to 1, and that's certainly less than 2, and then I also calculated S2, and that's less than 2. You could throw in S3 as another base case if you wanted, but our inductive hypothesis is going to be, assume that this is true for n equals k, that S sub k is less than 2. And now we need to use our inductive hypothesis to show that it is necessarily true that that k plus 1 is true. In other words, S of k plus 1 is less than 2. So we're going to look at what S of k plus 1 is equal to. And plugging in our formula, S of k plus 1 is equal to 1 plus S of k all square rooted. And now here, we're going to use our inductive hypothesis. We know something about S of k, and that is that it's less than 2. So that means this square root, the sum of what's inside, is going to be less than 1 plus 2, which means the square root is going to be less than 1 plus 2. And again, we got from here to here by using our inductive hypothesis. And so 1 plus square root of 2 is equal to square root of 3, which is less than 2. So S of n is less than 2 for all n natural numbers. So that was actually not too bad. It seemed like it was going to be something horrible, but it wasn't. So now that we've proved that Sn is bounded, we want to prove that Sn is increasing. And for this, we'll also use induction. Hopefully it's just as easy as our last proof. To show something is increasing, we need to show that Sn is less than or equal to Sn plus 1. So actually I need an equal here. So that's a good start. And since I said we're going to use induction, we have our base case for n equals 1. We want that S1 is less than S of n plus 1 is S2. And we already showed that 1 is less than the square root of 1 plus 1. So that's true. Now we're going to do our inductive hypothesis. We're going to assume that the statement is true for n equals k. In other words, Sk is less than or equal to S of k plus 1. So now we're going to use our inductive hypothesis to show if the inductive hypothesis is true, then it must be true for n equals k plus 1. In other words, plugging in k plus 1 for n, we want to show S of k plus 1 is less than or equal to S of k plus 2. So S of k plus 2 from our formula is equal to 1 plus S of k plus 1. But we know from our inductive hypothesis that S of k plus 1 is greater than S of k. And that will mean 1 plus S of k plus 1 must be greater than or equal to 1 plus S of k. So this here then is S of k plus 2. This is S of k plus 1. So we have S of k plus 2 is greater than or equal to S of k plus 1. And so we have in general that S of n is less than or equal to S of n plus 1, and S of n is increasing. Now we have shown that S of n is bounded above by 2. So we've shown this condition. We showed it is an increasing sequence. Again, it's a monotone sequence. So by the monotone convergence theorem, it must be convergent. To find out what Sn converges to, we're going to use the fact, and this is from 2 videos ago or from a different video, the limit of S of n plus 1 is equal to the limit of S of n. So it's this note here that I have for you. So S of n plus 1 is defined to be the square root of 1 plus S of n, and that's equal to the limit of S of n. Because the limit of square root of Tn is equal to square root of 2, I have substituted the Sn for S, and now I have just an equation for S, so I square both sides, I solve for the equation, and this is my limit for S of n, which is equal to S. And here again is the summary by the monotone convergence theorem. It is convergent, and the limit of S of n is equal to 1/2 plus the square root of 5/2, the square root of 5 over 2. Our next theorem, if Sn is an unbounded increasing or decreasing sequence, then the limit of Sn is equal to positive infinity if it's increasing, and negative infinity if it is decreasing. Our next example is to consider Sn defined by Sn equals 1, and S of n plus 1 is equal to Sn plus 1 divided by 4, the whole thing divided by 4. We want to find the first 4 terms, we want to show the sequence is decreasing, and then we want to use this to show it is convergent, and we want to find the value S of the limit. Here I plugged in to find the first 4 terms. And to show that Sn is decreasing, I need to show that Sn is greater than S of n plus 1, or equivalently Sn plus 1 is less than S of n. And like the other example, because our sequence is defined by a base case and then a recursive case where each subsequent S of n plus 1 is dependent on S of n, we're going to use induction to show that it is decreasing. And I'm going to do this using induction. So my base case, S1 is greater than 2. You can see from my terms here, or in other words, S2 is less than S1. 2, for my inductive hypothesis, I'm going to assume the statement is true for n equals k. That is, S of k is greater than S of k plus 1. And last, I need to show, using my inductive hypothesis, that n of k plus 1 must be true. That is, S of k plus 1 must be greater than S of k plus 2. I have S of k plus 1 is equal to S of k over 4 plus 1 over 4. But my inductive hypothesis, this S of k plus 1 is smaller than S of k, so this whole thing, S of k over 4 plus 1/4, is going to be greater than S of k plus 1 over 4 plus 1/4. Again, this is by my inductive hypothesis. And this part here, s of k plus 1 over 4 plus 1/4 is equal to s of k plus 2. So what I have shown is s of k plus 1 is greater than s of k plus 2. Hence, Sn is decreasing. Actually, I really should have said hence. This statement here is true that S of n is always greater than S of n plus 1, which means that Sn is decreasing. So far, we have shown that Sn is decreasing. Now we want to show that Sn is bounded below by 0, and once we have shown both it's decreasing and bounded, we can use the monotone convergence theorem. So to show it is bounded, we're going to use induction, and again, we're going to say it's bounded by 0. So the base case, n is equal to 1, so certainly S1 is greater than 0. We're going to assume for n equals k that S of k is greater than 0. And next we need to show for n is equal to k plus 1, that is S of k plus 1 is greater than 0. So S of k plus 1 is equal to S of k over 4 plus 4. And by the inductive hypothesis, S of k is greater than 0. So that means S of k over 4 is greater than 0, and of course 4 is greater than 0, which means S of k plus 1 is also greater than 0. Hence, we have shown that S of n is always greater than 0 for all n, so Sn is decreasing and bounded below. And since we've shown Sn is decreasing and bounded below by 0, therefore by the monotone convergence theorem, Sn is convergent. Oh, and just when you thought we were done, now we need to find the limit of Sn. Again, we're going to use this note here that the limit of Sn plus 1 is equal to the limit of Sn, so we have that statement written here. And then we're going to use our formula, very similar to the other problem we did, the previous problem. So Sn, we're going to plug in Sn plus 1 is equal to Sn plus 1 over 4 is equal to the limit of Sn. And then we're going to use our theorems about limits. So we're going to separate our limit out to the sum of limit of Sn over 4 plus limit of 1 over 4. The limit of Sn we're going to say is something called S. And now we have substituting limit of Sn is equal to S. We have this is S over 4 plus 1/4 is equal to S. Doing the algebra, we get limit is equal to 1/3. Again, this is exactly like our previous example. Now we are ready to talk about Cauchy sequences. So when a sequence is convergent, the terms get close to the value of the limit for large n. But by doing so, they also get closer to each other. So getting closer together is sufficient to imply convergence, and this is called the Cauchy property. So you can see as n gets large and Sn approaches the limit of 0, then the distance between the points, between 1 and Sn equals 1/2, is larger than the distance between these 2 points here, which is the 1/2 minus 1/3, and even smaller as you get to 1/4. So these points are getting closer and closer together as Sn converges towards its limit. And the Cauchy condition or property tells us that these terms getting closer together is sufficient to guarantee convergence. A sequence of real numbers is said to be a Cauchy sequence is if for each epsilon greater than 0, there exists a natural number capital N such that m and n greater than or equal to capital N implies that Sn minus Sm, absolute value, is less than epsilon. Using this series here as an example, I can choose epsilon equal to 1/2, and then I could choose my capital N to equal to 2. Then for any m and n greater than or equal to 2, I can see that the distance between any of these 2 points is less than epsilon. So for example, if little n is equal to 2 and m is equal to 3, I can see that the distance between these 2 points is less than 1/2. And the distance between, if I chose instead m equals 4, the distance between n equals 2 and m is equal to 4 is still less than 1/2. And again, since we approach 0 and never quite get to 0, the distance between n and m, any 2 points that I choose in here, will be less than 1/2. If I want to go even smaller, epsilon is equal to, say, 1/4, then my n has to be bigger. It probably has to be something over here. If I wanted for epsilon equal to 1/4. But no matter how small I choose epsilon, I can just go further out to find a capital N that will satisfy this condition. So that's what it is to be a Cauchy sequence. You will notice the similarity in the definition of a Cauchy sequence with the definition of convergence of a sequence. And really that's no surprise because in both cases we're talking about a sequence converging to a limit. So also is no surprise, our proof strategy is going to be very similar. And I'm not going to put this on every page, and I also kind of just did it very briefly so that you can have an idea of what's going on, but you might want to write this down and give it some thought. But essentially, you start with Sn minus Sm is less than epsilon. You're going to algebraically manipulate this expression to an inequality with only one variable, either the n or the m. And it's not that you so much eliminate it, well, you do eliminate it, but basically you're using inequalities to do that. We're going to do examples. And then you solve for either n or m, whatever left, in terms of epsilon, and you're going to use this as capital N. And then you plug in your capital N into your proof template, and then you work the calculations backwards until you go from the calculation from n up to Sn minus m is less than epsilon. We will do a couple more lemmas before we get to an example of a proof. We have the lemma that every convergent sequence is a Cauchy sequence. And the other lemma, every Cauchy sequence is bounded. And then from here, from every Cauchy sequence is bounded, we can get the Cauchy convergence criteria theorem. A sequence of real numbers is convergent if and only if it is a Cauchy sequence. Our first example is to show the sequence given by Sn is equal to n over n plus 1 is a Cauchy sequence. To start my proof, I'm going to look at the absolute value of Sn minus Sm less than epsilon, and this comes straight from my definition of what it is to be a Cauchy sequence. And when I started doing my example, for whatever reason, I named my sequences with a's. So I have an minus am is less than epsilon. Without lots of generality, I am going to assume that m is less than or equal to n. And now I'm going to look at the inequalities. So in particular, I'm going to do the algebraic manipulation of the expression here that I have here to eliminate one of the variables. So I'm left with either n or m, but so that I can do this by using inequalities. I have just written this algebraic expression here, and then I separate this out. Well, certainly this, since m is greater than 0, it is a natural number, then this algebraic expression is less than n over n plus 1, m plus 1. And then this algebraic expression separates out to n over n plus 1 times m over m plus 1. And since n over n plus 1, n is a natural number, this here is less than 1. That means this whole expression is less than or equal to 1 over m plus 1. And this is exactly what I mean by we're going to algebraically manipulate the expression until we have only one variable. In this case, we manipulated it until we only have m. And we did that by using these inequalities. So we kind of took this, we could immediately eliminate the m here, because when you subtract something from the numerator, you're always going to get something smaller as long as m is positive, which it is. And then here we eliminated it just by grouping all of our n terms together and seeing that it was less than 1. So then we can claim that this inequality is less than this other inequality. Anyway, so now we have only one variable. So now we can solve for n, or in this case m, in terms of epsilon. And now I can set this expression, which came, right, all of this inequality, this is equal to this, which is an minus am is less than epsilon. And now I can solve for m in terms of epsilon and use this as my capital N. And I'm going to be a little bit lazy and just say that I'm going to choose n in the natural numbers such that absolute value of 1 over n plus 1 is less than epsilon. And actually I can get rid of the absolute value sign since n is a natural number and greater than 0. And I can plug into my proof template. So given epsilon greater than 0, I'm going to take n from the natural number such that 1 over capital N plus 1 is less than epsilon. As I said, since n is a natural number, I can get rid of the absolute values. And then I know that if capital N is less than m and n, then I start with 1 over my m plus 1 is less than epsilon, and then I do all of these calculations backwards until I finally get to an minus am is less than 1 over m plus epsilon plus 1, which is less than epsilon, which is exactly what I wanted to show. And again, this proof should seem very reminiscent of proving a limit, because in essence, that's exactly what you're doing. And therefore, you have shown that this is a Cauchy sequence. And now I'm going to do part of the proof of the Cauchy convergence criteria, which says a sequence of real numbers is convergent if and only if it is a Cauchy sequence. Because of the if and only if, there are two directions to prove. We're going to start with the forward direction, which is to assume it's convergent, and then we want to show it as a Cauchy sequence. Since it is convergent, we can set, suppose that we have our series Sn and that it has a limit S. And we're given that epsilon is greater than 0, and we need to find that natural number, capital N, and that satisfies this condition here for a Cauchy sequence. For this example, since I don't have a formula for Sn, in other words, in our last example, we said Sn is equal to n over n plus 1. Since I don't have a formula for that, I'm not going to follow this, this next step, but what I'm going to do is look at Sn minus S, and I'm going to set that less than epsilon over 2, because I'm going to do something similar for Sm, and so when we add them together, the two epsilons over 2 is just going to be, I'm going to keep something less than epsilon. So now when I look at the absolute value of Sn minus Sm, I can then add and subtract an extra S. And by doing that, then I can separate these two out and use the triangle inequality. So now I'm going to have Sn minus S, and I'm going to have S minus Sm. And by the triangle inequality, this absolute value is less than or equal to the sum of the two parts. And then this over here, my Sn minus S is less than epsilon over 2, and my S minus Sm, because this is just an absolute value, and here I have Sm minus S, is also less than epsilon over 2. And when I add these two together, I have this is equal to epsilon, so I have Sn minus Sm is less than epsilon from all of these inequalities. And then you can plug it into your proof template. I am not going to do the proof in the other direction, which is assume it's Cauchy and show it's convergent, but I do have the proof here for your reference. And we start by showing that Sn is bounded. And then once it is bounded, we're going to use the Bolzano-Weierstrass theorem to go ahead and complete the proof to show that it converges. For an example of the Cauchy convergence criteria, which again is that it's convergent if and only if it is a Cauchy sequence, we're going to use that to show the sequence given by this S of n is divergent. And just to write out the first few terms, S1 is equal to 1, S2 is equal to 1 plus 1/2, S3 is equal to 1 plus 1/2 plus 1/3, etc. And note that this Sn is different from the Sn is equal to 1 over n, because this is the sum of all these terms, whereas this is just, Sn is just equal to 1 over n. And I did plot this for you and talk to you about how this was a Cauchy sequence and also converges to 0. Whereas this sequence we're working on now is divergent and also not Cauchy. So now I've written Sn and Sm in terms of my formulas. Without loss of generality, I could assume that m is greater than n. So Sm I'm going to say is equal to 1 plus 1/2 plus 1/3 up to 1 over n plus 1 over n plus 1 all the way up to 1 over m, again because m is greater than n. So when I subtract, when I look at this Sm minus Sn, I can look at Sm here minus this Sn. So I'm going to be left with the terms 1 over n plus 2, 1 over n plus 2, all the way up to 1 over m. And now because all of these terms before 1 plus m is greater than 1 plus m, then this whole sum is greater than 1 over m done m minus n times. So this here is greater than m minus n over m, which is equal to 1 over n over m. If this sequence is Cauchy, then that means from the definition of Cauchy, for every epsilon greater than 0, and for every m and n greater than capital N, this absolute value has to be less than epsilon. However, when m is equal to 2n, this Sm minus Sn here is always greater than 1 minus 1/2, which is equal to 1/2. So in other words, no matter how large your n is, you can go out to 10,000, 100,000, whatever it is. So if little n is equal to big N, then m is equal to twice as much. By the Cauchy sequence, for all natural numbers m and n greater than n, you have to have the distance between n and m arbitrarily small. And in this case, the distance between m and n, as long as m is equal to 2n, is always going to be greater than 1/2. So you cannot get an arbitrarily small distance between any two numbers, any two sequence elements whose index is greater than some number capital M. And therefore, Sn is not a Cauchy sequence, therefore it does not converge, i.e. it diverges. We have reviewed the definition of convergence. We talked about monotone sequences in the monotone convergence theorem, which said a monotone sequence is convergent if and only if it is bounded. We talked about unbounded sequences and said their limit was plus or minus infinity. We talked about Cauchy sequences, which are sequences that the terms get closer and closer together as n becomes very large. And we said that we did the formal definition, and we said that every convergent sequence is a Cauchy sequence, and every Cauchy sequence is bounded, which gave us the Cauchy convergence criteria. A sequence of real numbers is convergent if and only if it is a Cauchy sequence. And I just wanted to also note that Cauchy convergence depends on the completeness of the real numbers, since the proof uses the Bolzano-Weierstrass theorem. Here is a problem for you to try for review. It does have a few parts in that you want to prove it is bounded, then you want to prove it is monotone, and then you want to find the limit. So I only did one review problem. Pause the video, give it a try, and on the next slide I'll have solutions for you. Here is the proof that the sequence is monotone increasing, and I use induction as I had suggested in my proof strategies. Here I have proven that Sn is bounded, and I chose an upper bound of 2, that you could have chosen a different upper bound. And again, I used induction as one of my proof strategies. And here I used the fact that it was bounded and monotone, and I invoked the monotone convergence theorem to say that it is convergent. And then finally, to find the limit, I used this fact up here in my proof strategies, and this is my limit, s equals 7/4. And that is it for this video. Thank you for watching.